Bam. Welcome back to Mr. Powers Teaches Algebra. Yeah, I guess. We've been talking about binomial theorem, the good old-fashioned binomial theorem. We got binomial theorem stuff up here. And what that does is, and we're getting there today, we're going to start off here by stating the binomial theorem. Yesterday was trying to see some patterns and be able to confidently derive the binomial theorem. And I think we were able to do that yesterday. And then today we're going to go ahead, we're going to state what we can find out from our little investigation yesterday, and then link it to this neat thing called the Pascal's triangle. And that will be maybe in the next video. So let's see how this goes. Again, the binomial theorem just helps us do these expansions like x plus y to the fifth, or maybe something like 2x minus 3y to the eighth, and actually multiply all that out. Like, oof, we don't want to do that. It's going to be a lot of work. But there's a shortcut, and that shortcut is a binomial theorem. So I did show you a little bit of Pascal's triangle without explaining it. And we did see that if we expand, like, say, x plus y squared, it is the second row. We call this row 0. 1, 2, 1. We see that 1, 2, 1 pop up. And with x plus y cubed, we see a 1, 3, 3, 1. And that is also in our third row of our Pascal's triangle. So we see these patterns here, but we haven't explained anything yet. We see some things. So we're going to prove these things in a bit. And when we're doing both of these, x plus y cubed, what we noticed was there's some counting. There's like, hey, how many ways are there to get 1y? If we take one from here, one from here, one from here, how, an x or y, an x or y, an x or y 3 times, how many ways are there to get 1y? Well, there were 3. How many ways are there to get 2 y's? There were 3. How many ways are there to get all 3 y's? There's only one way. And we notice that by distributing, we are finding all the possible outcomes for this kind of thinking, right? There's 3 terms here. There's 3 factors, I guess, x, x, x. Here we have x, x, y, x and 2 y's and all y's, right? And we get every single outcome when we do this distribution. And so we can use this kind of thinking. And it works out in a lot of ways you think about it. We got 3 choices. Each one has 2. How many possible outcomes are there? 8. And there are 8 individual terms if we do the distribution without combining like terms. So this is really fascinating, and that's the investigation we did in the last video. So if we have that connection down now we can say that we are finding these combinations. Here, how many ways to get 0 y's? 1 way. How many ways to get 1 y? 3 ways. How many ways to get 2 y's? 3 ways. And how many ways to get 3 y's? 1 way. I think how many ways to get 1 y? There's 3. And so that must mean that we're seeing combinations here in Pascal's triangle, and we're seeing them in these terms. And so we can use that thinking to come up with a formula for these. And so that formula is right here, you guys. First off, n and r integers greater than or equal to 0 with n greater than or equal to r. The binomial coefficient is n choose r. We say this, or we can use this notation. I believe Desmos kind of writes it like this. Or lots of times in textbooks, we'll see it like this. N choose r. And we like to say n choose r. How many ways are there to choose r things out of n things? Okay, which is what we're doing. And so x plus y to the n is x to the n. And then that first term is how many ways are there to pick one thing. So again, we could think about the y's. How many ways to pick 1 y out of n y's? Or out of n terms, right? It's the same thing. Well, there's x to the n minus 1 times y. and choose 1. And we saw that in our examples when we had 3. How many ways are there to pick 1y out of 3? There's 3 ways. We had 3 right here. 2 y's out of 3 choices, right? 3. How many ways are there to pick 3? This is 3 choose 3 is 1. So we see that pattern here. These are the exact same things. And so we do see that this here, this coefficient is 3 choose 0. Or you could say 3 choose 0, however you want to do it. That's the same as 1. This guy here is 3 choose 1. This guy here is 3 choose 2, right there. And this guy is 3 choose 3, right there. How many ways are you to get 3 y's in 3 choices? Well, there's a y and a y and a y. That's only one way to do it. So we got 1y cubed. All right. So we do see that. And the simpler term here too. We saw this, and you can check these. 2. This is n equals 2. 2 choose 0. So choose no y's in this case. There's one way to choose no y's, right? 2 choose 1. How many ways there to choose 1 y? There were 2 ways to do that. And then 2 choose 2. How many ways are there to choose 2 y's? There's only one way. We had 1 y squared. And so we did see this pattern. We definitely see why it's happening with these tree diagrams. So I think we're confidently can say this is exactly what's happening in these things. All right? And so this is our little formula that we have. Okay? So we can break this up here a little bit. We got this piece here. This is the shortcut way to write it. We're using sigma notation. And then here's the long way, just spelling it all out. And what they don't show here is that this is really n choose 0, which is always equal to 1. And right here is n choose n, which is also always equal to 1. So the pattern does continue for every single term. And so the r plus 1th term of the binomial expansion, and this is a handy little trick, of x plus y to the n is n choose r, x to the n minus r, y to the r. So really, really quickly, let's use this to do an example. Okay? Let's do an example of this. We can easily do this pretty quick. All right, so here's a problem we can try this on. Okay? And this will be super easy. So when it says r plus 1th term, we want the 5th term. So in other words, r plus 1 equals 5. That's what that means. And that means then r is going to be 4. And it makes complete sense, because if you look at the examples we did up here, this first term, we did 3 choose 0. The second term was 3 choose 1. The third term was 3 choose 2. So it's always one less than the term we are on, right? If we're looking for that coefficient, our choose is one less. So it makes a lot of sense why they're going to go ahead and just kind of say, hey, the r plus 1th term is n choose r, because r is always one less than the term we're on. Okay, so that's where that's coming from. And so that makes tons of sense. And then also, if we're looking at these examples here too, what's the power of our x or our y, let's say, right? our x is the same as the number of the term we're on. So second term, x is going to be 2. Third term, or first term, our x is n. Our second term, x is n minus 1. Third term, x is n minus 2. Our powers of the x are going down as we go along. Powers of the y's are going up. First term, the power of the y is 0. The second term, power of the y, is 1. So the power of the y is also the same as that choose. And so we can see that here also. That our power of the y is the same as r, and the power in the x is n minus r, because these always add up to n. That's another pattern we see when we're looking at especially the examples. 3, 2 plus 1 is our power in the y is 3. 1 is the power of my x here, plus 2 is 3, 3. So there's a lot of patterns going on here, and we can see why from our previous video, why that's happening. Okay. So back to there. No. Okay, back to here. Here we go. So let's do this problem. Find the fifth term in the expansion of x minus 2y to the seventh in simplest form. So we know r is 4. This is my a. This is my b. This is my n. If I know the formula, which is right here, it's easy. Or the way I like to do it is, okay, the fifth term, so it's going to be 7 choose 4 of, and then my power, my x, power on my b is going to be, so my b is negative 2y. That's going to be the same as the 4. And then my first part, my a here, which is x, is going to be 7 minus 4. So that's going to be 3. That's the way I like to do it. Or we can just plug it all in. We know all the values and figure it out. Piece of cake. Too easy. It's too easy. And that's going to be our answer. And then we just work that out. So I'm not going to go ahead and simplify this out. I think we can do that later. But that's going to do it for this one. In the next video, I'm going to show why the we're going to investigate our Pascal's triangle and see why is this Pascal's triangle actually giving us those same values as the combination notation. There's a reason why. There's a linkage there. And just a really quick mention, to get one row, you add the two numbers that came right above it. So to get this 5, that's 1 plus 4 is 5. To get the 10, that's 4 plus 6, that's 10. To get this 10, 6 plus 4 is 10. That's 5, 4 plus 1 is 5. And that's how I get every next row. So is there something like that true with combinations also? And guess what? There definitely is, which is a really fascinating thing. And that's why we can get all these values with Pascal's triangle. So we're going to make that connection next time. So until next time, enjoy doing math.